One of the wonderful challenges about astronomy is that we have to imagine something so we can go look for it. But nature has this way of being even more creative than we are. So we have always been surprised by what we see in the sky. That's why building a telescope has always been interesting. Every time we build a better one, we see something we never imagined was out there. That's been going on for centuries. This is the next step in that great series, the bigger, better, more powerful telescope that will surely surprise us in some way that I can't tell you.
Hello, and welcome to NASA Science Live, an opportunity for you to come behind the scenes and to get to know your space agency. I'm your host, Leslie Garrison, and this show is all about you being able to interact with NASA scientists and subject matter experts to get your questions answered. Visit us on Facebook or Twitter and ask us questions using the hashtag AskNASA, or you can simply leave questions in the comment box wherever you're watching this video. Today, we are going to be talking about a telescope that's like a time machine, the James Webb Space Telescope. It's set to launch into space in the year 2021 and to become the world's most powerful space telescope and complex. It will examine the atmospheres of distant planets and orbit other stars. It will help to solve the mysteries of our solar system and the place that we are in the universe. First up, our friend Sophia Roberts is going to take us inside the actual clean room where the telescope is currently being built. She was recently at Northrop Grumman's facility in California and filmed this behind-the-scene video just for you. It's not often that we get to go inside the clean room with our cameras where such a powerful telescope is being built. So sit back and enjoy the first stop on our journey to understand the extremely and truly extraordinary James Webb Space Telescope.
All right, so I've got my bunny suit on, which protects the space telescope from me and any particles that may come off of me. So we are at Northrop Grumman Space Park in Redondo Beach, and we're gonna go see the James Webb Space Telescope. So let's go. Right now, we're in a huge clean room, and like everyone else, we've all got on bunny suits. And this is NASA's James Webb Space Telescope. This telescope was envisioned shortly after Hubble's launch to continue on the next phase of questions about our universe. It's going to look in the infrared spectrum of light and then seek the light of those really early forming galaxies, and then try to answer the questions about our universe. And so what we're witnessing right now is the two major halves of the telescope being put together. What's really exciting about what's happening right now is that we are in the final stages of construction. So above us, we've got the optical portion of the telescope, which has just been integrated with the other bottom half, the sun shield and the spacecraft bus, which is just below it. But let's continue on. And coming around this side is the most spectacular view of this whole thing, because you can see there are these 18 gold mirrors. They are real gold. And the reason is because gold reflects infrared light the best. Webb is going to try to solve the mysteries of our solar system. It's going to look to worlds around distant stars, and then look at the mysterious structures, and then try to explain the origins of our universe. And no project like this can be done alone. So Webb is an international program. It's led by NASA with its partners, the European Space Agency and the Canadian Space Agency.
Thank you so much for taking us inside the clean room, Sophia. I am in awe at just how large and beautiful that telescope really is. Absolutely incredible. So our next stop on this tour of the James Webb Space Telescope brings us back to Northrop Grumman's facility, where NASA Administrator Jim Bridenstine visited the telescope just last week. Let's hear about what it's like to see the fully assembled observatory in real life.
Hey, I'm Thomas Serpoken, Head of Science at NASA, and I'm here with Administrator Jim Bridenstine. We're in Redondo Beach, with Northrop Grumman in Space Park, and right behind us is the James Webb Telescope. How does it feel to be next to this huge telescope?
Oh, it's fantastic. You know, the James Webb Space Telescope is the most complicated spacecraft that's ever been built. And I know people watching on TV or on the internet can see it behind us right now, but I can also tell you a picture does not do it justice. When you are in the presence of this massive spacecraft, it will change how you perceive how complex and important this particular mission is. What we're looking at here are two separate elements. You've got a spacecraft element and the scientific instrument. And now they have been put together, both physically and electrically, in a way that was a lot of risk. This is a big day, and I want to say thank you to our partners at Northrop Grumman, but also thank you to all of the countries that have been involved in this. We're talking about 14 different nations that have been involved in producing this magnificent telescope that is really going to transform how we see the universe.
You know what's so amazing to me is, as an astrophysicist, is really seeing the first galaxies, the first stars that are right out there at the very beginning of many generations of stars that have created our environment.
That's the number one objective out of the gate. Imagine being able to see back in time. This isn't just looking deep into space, we're looking back in time.
Another element of that will be focused on exoplanets, planets in the outside of the solar system. How do you feel about those?
It's amazing. And when we talk about what gets the American public enthused about space exploration, or in fact humanity at large, it is the idea that we could find life on worlds that are not our own. It's never been done before. And that's really what we're going to be able to do with the James Webb Space Telescope. We're going to be able to see those atmospheres and make assessments. Is there water vapor in the atmosphere? Is there carbon dioxide in the atmosphere? And so I think that's so exciting about what James Webb is going to help us do.
Yeah, we know from our Earth, right, that when life came to be, the entire atmosphere changed.
Yeah.
And really seeing those changes in some of these planets that are out there, it's just going to be such a super discovery. Now, you look at this telescope, it's clear to anybody who stands here, this is complicated. There's a lot of people, thousands in fact, who put their heart and soul into this.
This is the most complicated spacecraft that has ever been built in human history. Hundreds of moving parts that all have to work, which is why mission success is the number one priority. We have to get all of these moving parts working correctly. This spacecraft is going to be 1 million miles from Earth, on the other side of the moon, as a matter of fact. So what that means is we're not going to have access to it once it's there. We have to make sure that it's right from the beginning.
So one of the elements that many people forget is some of the technologies that were developed here actually have already had an impact on our lives. Do you know an example or something that's in your mind?
Yeah, so some of the sensors on this particular spacecraft have been used for, in fact, surgery. LASIK eye surgery, for example, has benefited from the technology developed for the James Webb Space Telescope. So these are spin-offs. These are capabilities that come from NASA's investment into these kind of activities, and they can't be dismissed.
We're just about out of time, and I want to thank you with many regards here from Redondo Beach, from Space Park.
Yes, Thomas, it's been great. Congratulations to you and your team on getting this far, and I cannot wait to see the end result.
Thank you so much.
That was a fascinating discussion with Dr. Z and Administrator Bernstein, and an interesting perspective from an astrophysicist and from NASA Administrator. So, welcome back to the studio. I'm joined here with a NASA scientist, Amber, from NASA Goddard, and an engineer, Keith, who's also here at NASA Goddard, who's going to tell us more about the amazing telescope that's being described as a time machine. But before I dive into the challenging questions, I have a personal question to ask. So, Keith, Amber, while the telescope was actually here at Goddard, did you actually have the opportunity to go inside the clean room, just as Sophia did, and actually work with or work on, touch the actual telescope?
Well, no touching, for the most part. So I'm a scientist. I'm an astrophysicist. I'm just a scientist. I'm not an engineer that's actually building the telescope. But I have had the chance to go inside the clean room, and it was incredible. I mean, it's so hard to describe how big and how beautiful this telescope is. And so I have had a couple of chances to put the bunny suit on and go inside and get up close, and it's spectacular.
Well, even us engineers aren't allowed to always touch the hardware, so we have highly skilled technicians that do most of that. But I had the chance to go in several times while the telescope was here, and you know, as we just said, it is remarkable. As you saw in the video right there, clean rooms are construction sites. There's people everywhere, there's wires and cables, so try not to go in there unless you absolutely have to, but when you do get to go in there, it's absolutely awesome.
I'm sure. One that you'll never forget, and definitely one for your career journals to read over and to share with your kids. And so we've already had the opportunity to talk a little bit about the actual James Webb Telescope and what we'll do, but Amber, inquiring minds really want to know, what's the actual goal of this mission?
Well, it has a lot of goals, and the goals are broad and they're big. And the telescope is basically designed to be the scientific successor to the amazing Hubble Space Telescope. As awesome as Hubble is, there's a lot of ways that we've sort of pushed it to its limits. And so what we're planning to do with Webb is push beyond what we've been able to do, even with the amazing Hubble, and answer some of the biggest questions in astronomy today. We want to look back and see some of the very first stars and galaxies that were born in the early universe. We want to study planets within our own solar system, and also planets orbiting other stars outside of our solar system. So we're talking about the entire breadth of the universe, from our cosmic backyard of the solar system all the way out to parts of space that we've never seen before.
Amazing. So, Keith, let me come over to you as the engineering, on the engineering side. What part of this time machine will support the actual science that Amber just spoke to us about?
Sure. So the most unique feature about James Webb is that it's extremely large, with a very large optical main mirror. And the other interesting feature that enables that science is that it's an extremely cold operating telescope. We have to cool this telescope down to what is roughly around 50 Kelvin, or about minus 380 degrees Fahrenheit, in order for it to operate and detect the wavelengths of light that our scientists are seeking. And that wavelengths of light are in the infrared. So it's really trying to detect really tiny heat signatures from these faraway objects first born in the universe. And in order to do that, we have to get it cold. So when it's cold, it does not see the heat from itself. So that's the two big things. It's large and it's cold.
It's large and it's cold, great. So, you know, I'm always astonished at the science and the engineering of NASA missions. There's nothing like it. So let's step away from some of my questions and let's take some of the questions that are in queue from #AskNASA. So, Doug Curie on Twitter asks, what molecules might the James Webb Telescope be able to detect on its journey, and how clearly could that indicate life otherwise?
That is a great question. And of course, one of our big questions, not only as scientists, but as humans, is there life in the universe? And this telescope, the Webb telescope, is definitely our next big step on the journey to try to answer that question. So in terms of the specific molecules that we'll detect in some of the exoplanet atmospheres, we'll be looking for things like water vapor and carbon dioxide and methane. And it's just sort of, it's good luck that those types of elements, those molecules, exist in the infrared part of the electromagnetic spectrum that Keith has mentioned already. And so we kind of lucked out. You know, infrared's going to help us find these amazing molecules in the exoplanet atmospheres that could possibly signal a planet that's habitable, or that is definitely the next step in that journey. Now, in order to do that, in order to really detect a planet that we can say, yes, this planet could have life, we'd have to get really lucky. So we're definitely not saying that we're going to find life with this telescope, but we can definitely say that this telescope will do amazing things in exoplanet science, and that it's definitely our next big step on that journey in our search for life in the universe.
Great, that's awesome. So let's take one more question from #AskNASA. John in Mexico on YouTube asks, is the telescope going to be able to view all signs of space, or will it be prohibited by the sun?
Actually, the way we configure and the telescope with this large sun shield, we put it about 1 million miles away, as the administrator mentioned. That lets us keep the telescope always pointed to deep space. So over a course of a year, we get the full sky. We can see anywhere. We can point anywhere over the course of a year. And if at any given time, I think we can see just about 60% of the sky. So yes, the telescope is not limited, unlike with Hubble, where it's going around the Earth every 90 minutes. James Webb will be operational almost 24/7.
Okay, so continue to send your questions in using hashtag AskNASA on Twitter or Facebook, and we'll try to get them in. So, okay, let's just continue, and don't exhale too quickly because I have some more of those questions. But Amber, Keith, let's talk a little bit about those 18 iconic gold mirrors that are actually on this telescope. Amber, can you tell us about the science behind those mirrors? And then Keith, I would like for you to tell us a little bit about the engineering behind those mirrors.
Sure thing. So the reason the mirrors are gold in the first place is because gold is a good reflector of infrared light. So we've already talked about how Webb will view the universe in the infrared part of the spectrum. And that means it will see light that's just a little bit more red than visible light, than what your eyes can see. And so it turns out that gold reflects that type of light really well. So that's sort of the science behind why the mirror is gold.
Great. All right, so Keith?
Yeah, so we mentioned earlier that we want this primary mirror, this main mirror, to be really large. It also needs to be lightweight because we have to launch it into space. So if we looked at glass, we looked at other materials, and the best material for this telescope was beryllium, because beryllium is really good at the operating temperatures that we like. So these mirrors are made out of beryllium, and then when you start looking at how to manufacture a large mirror like this, these 18 segments, each one of those segments was about the largest segment we could manufacture. So when you take the size and you can take the mirror segment size, that's how you end up with basically 18.
Great. And so as you've heard throughout this episode, Webb just completed a huge milestone by having its two halves connected for the very first time. So let's take a closer look at what it was really like. So just know that you've had the opportunity to explore and see an amazing process of joining Webb's two halves together for the very first time. As we've learned today, Webb is an extremely complex telescope, and it is being built to answer some of our biggest questions about the universe. As a result, engineers had to find a way to actually fold up the Webb so that it could fit inside a rocket for launch. But once it is in space, it will bloom into a full-size observatory. And Keith is currently at our Hyperwall, and he's going to explain the beautiful transformation that Webb will undergo once it's in space. Keith, take it away.
Thank you, Leslie. Well, I'm really excited to show this short video of exactly how that all happens. So we launch on an Ariane 5 rocket out of the French Guiana spaceport in South America, and it takes us about 25 minutes to get to orbit. And you can see the very first thing we do is we deploy our solar array. This is pretty typical of most spacecraft. We need to get that solar array out in order to start providing power. Up until this point, we've been on batteries, so it's very important. So that's the first thing we do is we put that solar array out. And as you can see, we're actually condensing this quite a bit. We're 20 hours into the mission here, and down here you can see the scale and how fast we're moving over that one-day period. So we do a mid-course correction where we actually fire our onboard propulsion system to correct any of the trajectory areas that Ariane may have provided, but they're going to put us right on target. Now you can see the real fun stuff starting right here. We start deploying our sun shield. So we have these 5 layers of our sun shield, and each one of all those 5 layers are supported during launch in what we call our pallets. These pallets assemblies actually hold and secure them for launch. And you can see that's the first thing that we put down. Much like a tray table on an airplane, that's how they fold down. You'll see our telescope extending up we want to get this telescope away from the spacecraft, because remember, this spacecraft is cold and our spacecraft is warm, so we want to separate it. After we roll up some covers that protect those 5 membranes during launch, then we'll actually start deploying out the 5 layers. Now, these 5 layers are fan folded up together, and we use something called a telescoping mid-boom, which is a lot like a selfie stick. We extend that out, and it actually drags all that material out. So we do that on each side, and the video is stopped right here because when we talked about those cryogenic temperatures that we want this telescope very cold, this kind of gives you orientation. We have the sun coming in down here, so it's always providing power. This sun shield separates that telescope from that sun, and this 5-layer assembly, you can start it back up now. You can see that we tension this up, all 5 layers, to create separation between them. And it's this separation that allows all that heat from the sun to escape before it reaches the telescope. We deploy something called a NAT flap, which helps us balance solar pressure. And then the last thing we do, once we get that sun shield out, we do start up some electronics, but the big deployment here is our secondary mirror for our telescope that's been stowed up. It sits on a tripod assembly. And we have those 18 mirror segments, but we fold 6 of them back. It's almost like a drop leaf table. So we unfold 3 of those, they fold forward. And then the last thing we do is we fold the other 3 forward like that. So as you can see, 29 days, I just covered in about 3 minutes. So I'm very excited to take some questions that on anything about James Webb. Back to you, Leslie.
Thank you. That's quite a dance that Webb has to perform as it travels 1 million miles from Earth, 30 days, full deployment. So thanks for walking us through that, Keith. Okay, well, Amber, it looks like Keith has really piqued the curiosity of our viewers, and we have a lot of questions in queue, so let's take them. All right, so Katie on Facebook asks, how does Webb get to its final destination, and how does it stop in a specific spot?
Okay, so like I mentioned there, we launch on an Ariane 5, and that Ariane 5 puts us on a trajectory straight out about 1 million miles away. So that's 4 times the distance of the moon, and it's opposite the sun. So we're on that trajectory about 1 million miles away, and actually it's almost like going up a hill. We start out very fast, and as we get further and further from the Earth, we actually start slowing down. And what we want to do is we want to put just enough energy in the James Webb as it leaves the Earth so that it stops right at that L2 point, or the 1 million mile away from Earth point. And then we actually don't sit at a point 1 million miles away. We actually go into an orbit that's actually an orbit around the sun, but the Earth actually drags us a little bit. That keeps that alignment between the sun and the Earth and James Webb.
Wow, that is amazing. So let's take another question. Ryoba on YouTube asks, is the James Webb Space Telescope going to focus on black holes?
Oh, yeah. So black holes are one of these amazing, mysterious things in the universe. There's a lot about them we don't understand. But we will absolutely be learning lots of new things about black holes with James Webb. So one of the primary science focuses of Webb is to study and learn more about how galaxies change over time. So if you look at galaxies in the very early universe, they look very, very different than the galaxies we see today in the nearby present-day universe. And so understanding how that change takes place over time is one of Webb's key goals. And we know that black holes play a major part in how galaxies change over time, because every giant galaxy that we know of has a huge black hole at the center, but we have no idea how they got that big. And one of Webb's key sort of questions that we want to answer is, how do black holes get so big?
Wow, fascinating. Go NASA. So we've learned a lot about this telescope that's like a time machine, but I'm really interested to hear about what's going to happen between now and the actual time that it will launch in 2021. So we know that the 2 halves have been connected, but Keith and Amber, can you actually take a step-by-step timeline? What's going to happen from now until 2021 liftoff?
So as you saw in the video, we just put the 2 halves together. So we're really excited that we have a full observatory. Both of those halves have been extensively tested. Now that they're together, we're going to spend most of 2020 testing the observatory as a single thing now. So we're really excited about that. So 2020, what we're going to do is we just unfolded and deployment tested everything you saw in the video. We're going to fold it back up, and then early next year, mid next year, we're going to subject it to the environment of the rocket. So the rocket shakes and creates a lot of noise. So that's called an acoustic and a vibration test. So we'll shake the entire observatory, we'll acoustic test it, then we'll bring it right back into that clean room and do all of our deployments again to make sure that we can deploy successfully again. All along the way, we're doing electrical testing. So we're always making sure the instruments are working, the electronics are working, the spacecraft components are all working. And then late next year, once we complete that, we'll start folding it back up again. We'll pack it up into its shipping container, and sometime late next year, we'll start the process of shipping it to the launch site, as I mentioned, at French Guiana in South America. And we actually do that transport via a ship that'll leave Los Angeles and then arrive down there. So that'll be early 2021.
Great. And so several times you mentioned testing and retesting. And so when we are talking to students about the NASA engineering design process that we feature in NASA's Best, we actually talk about how often we have to test the products, because once it's launched, there's no calling it back and saying, hey, bring it back, we have to do that over again. So that's really important. But we have some questions still in NASA hashtag, Ask NASA, and I would like to jump to just quite one or two if we have time. Why does the sun shield need 5 layers?
Oh, yeah. So 5 just turned out to be just the right number. So to put a little bit more information on it, 5 layers is what allows us. We need about a 500-degree temperature drop over that roughly 6-foot tall layers. When they're all spread apart, it's about 6 feet. We need a 500-degree Fahrenheit temperature drop. So that's really what dictated 5 layers. We looked at putting a 6th layer. That adds complexity, and it really didn't buy us much as far as temperature drop. The temperature drop from the warmest layer that faces the sun, it gets more and more difficult to get that temperature colder as you move to the colder layers. So we could have added a 6th layer. Would have helped a little bit, but it wasn't worth the complexity. But 4 layers wasn't enough. So these studies were done a long, long time ago. And 5 just turned out to be the right number.
Just happened to be the right number.
Be the right number.
Right. So I have a quick question. Well, I have a question that needs a quick answer. So John on YouTube asks, what are the operational temperature ranges? And Keith, I think you mentioned that earlier. So can you just elaborate on that for maybe 5-10 seconds?
Our telescope, like I said, we like our telescope to be right around 50 Kelvin. That's minus 360 Fahrenheit. So when you hear on the weather, it's minus 20 in North Dakota, that's nothing. We're at minus 360 Fahrenheit. It's almost hard to imagine. We actually have instruments that run colder than that. So we actually cool all of our instrument detectors to 30 Kelvin. And then we actually have one instrument that actually operates at 6 Kelvin. So it's very close to absolute zero.
Right, and just to imagine that, I think I'm cold when it's 32 degrees. Right. All right, so it looks like, oh, that's my cue. Looks like we're here again at the end of another episode of NASA Science Live. Time really does seem to fly when you're having fun, and when you're talking about NASA, I'm probably guilty of, being partial. But nonetheless, I want to take this time to thank you for joining us today, sending in your questions, and I especially want to thank our studio guests, Amber and Keith, for taking time to answer your questions. So I just want to again point out to you that you can always look for questions and answer on www.nasa.gov. And so in the meantime, until next time, continue to reach beyond the stars that you can see, but there's a lot more to be explored and discovered.